This is going to be the 3.1. I'm just going to kind of talk over what is in that other video. Just so hopefully we can have one video of 3.1 and not have to do it in different parts or chunks. 3.1 is basic concepts of probability and counting. I am just going to read these, so if you need to write this stuff down, you can take pictures of these if you need to after class. Probability experiment is technically what it sounds like. It's an experiment where you're just testing to see what the probability of an event is happening. So there's action that you put into it. You could do trials, and you end up getting certain results. It's either counts, measures, or responses, and all of those are obtained within the experiment. We have what is called an outcome, which is the result of a single trial in a probability experiment. It's a little cold. And then we have a sample space. The sample space is actually the set of all of the outcomes in a probability experiment. And then we have our event. An event is actually going to consist of one or more outcomes, and an event is a subset of the sample space. I did these just in case on my math lab, if it asks you certain questions, like you literally have verbatim everything written down. Okay, because they will, I've noticed whoever created this course, like at the beginning, they have those definition problems. Okay. They do ask a lot of, and believe it or not, I don't want y'all to open up the homework until we've covered everything, because after I cover stuff, I like to look at the homework and then be like, we didn't cover that, and like, I want to delete things. So, and that's because I went ahead and shut down the majority of them. I did, so it's like, don't do it until we cover it, because like there'll be 30 problems of stuff that's just way harder than y'all need to do. And like I want to get rid of that and make it, 10 or 15 problems of only what we cover. So always tell me if it's something really crazy. We'll either talk about it or we'll 86 that problem. They did. That could be because I synced everything and it's waiting. We'll talk about that because it could just be because my math lab and Canvas haven't been talking correctly to each other. And when I go in and I'm like, hey, sync these homeworks, it might kind of mess up what it's sending. So we'll do a comparison. We'll make sure everything's okay. So an example of a probability experiment. This is a survey was, no, doesn't say that. It says a survey asked people for their blood type. The different blood types are O, A, B, and AB. And they also want to know whether or not you have positive or negative blood. And then it wants us to determine the number of outcomes and identify the sample space. And all of this is what we did. I just want to have one video of 3.1 if possible. Don't even have to get these notes later. Okay, so the solution to that blood type problem would look as such. So the different blood types we have are O, A, B, and AB. And then because they want to know if you have O positive or O negative blood, and that actually goes with each different type. Whenever you get to the very bottom, you notice that you have all of these different outcomes. It wanted to know the sample space, and it asked you the number of outcomes. So the sample space, okay, so a sample space is a set, and I think I wrote this on the last thing. These are braces, right? And braces denote a set. So whenever it wants you to do the set of something, of the set of all your outcomes, right? Set means that it's braces, and a sample space would be as a set. So you start. We would say that the sample space is the set of all of these individual blood types. And if you notice, whenever you list your sample space, each individual outcome needs to be divided by commas. Okay, so just make sure that you keep that straight. And then it does ask you to figure out the total number of outcomes, and we had 8, because if you add those up, you get 8. Okay, and then we had the difference between like a simple event and an event that wasn't simple. They talked to us about like tossing a coin in the air and then like rolling. They say die. I always say dice. Dice is 2, die is 1. But if I toss a coin, I've got either tails or heads. And then whenever I roll the coin, there's 6 different outcomes because it's a 6-sided die. So like tails and then getting a 1 on my die we called it T1. And then T2 was getting a tails and rolling a 2. And then H3 was like flipping and like getting a heads, tossing it, and then rolling and getting a 3. So we had that little diagram, and then we did these little examples. Simple just think of a simple event is just one single outcome. So an example was like tossing heads and then rolling a 3. So they called this sample space, or not really the sample space, but they called this like event occurring, they called it A, right? So they said this event of tossing a heads and rolling a 3, call that A. When does that happen? What's the actual sample space of that? And if you look, heads and 3 happens one time at H3. So we would have in braces H3, and we could conclude that this is a simple event, because there was one outcome where that happens, right? And then we have an example of something that's not a simple event, and it says like tossing a heads and then rolling an even number. So if you look at tossing a heads, sounds funny saying that, and then you look at even numbers, that's going to be 2, 4, and 6. So there's 3 outcomes to that event, which would imply it is not simple because it actually had more than one outcome. They called this event occurring B, and the sample space is equal to H2, H4, and H6. Therefore, not simple, because there's not a single. Okay, I really don't even know what else we do for this section, but we're going to go and start. Okay, well, obviously, more probability. That's actually what we're doing all in chapter 3. It's all probability. Okay, so let's start. There's a note that we go ahead and start the next page with. It is actually a very, very important note. Okay, there are questions in the homework, and like there would be questions on the test, because it is very important to understand this. It's not hard, it's very simple, but it's just important. Okay, so the note that we have here is the probability of an event Tony, do you want to come and get these previous pages? Take pictures of them, or just to, yeah, you're going to do that? And that way you maybe pick up right here, and then you could already have these to copy from. Actually, you know what? These came from what we did in class. You can keep those, and then this will be my key. Is that good? Okay, the probability of an event cannot be negative or an improper fraction. Very simple idea, very meaningful concept to understand. And so it's like, why can't it? If you really think about it, it's like, what's the probability of you winning a game or you doing something and like, oh, you have a negative 3.5 chance? Like, that really does not make any sense. I kind of just show that with a little baby line, little baby number line. Okay, right here, just kind of like that. Okay, and then on the left, I'm going to do a tick mark or a notch. And on the far right, I'm going to do one. Underneath the left is 0. Underneath the right is the number 1. Might take a second to focus. Y'all, our probability of any single event at all ever has to lie in between 0 and 1. And so the way that they do this, and they'll actually say that it lies in between 0 and 1 inclusive. Inclusive means that 0 and 1 are included, right? So this is what they do. They'll say that 0, I'm going to write this right on the top of the number line, right in between these zeros and ones. 0 is less than or equal to, and then, okay, so it's like a capital P, open, put a capital E, and close. That actually is saying the probability of an event. The probability of an event lies within 0 and 1. Okay, so it's actually, the probability will always be greater than, and it can also equal 0, and then at the same time, it'll always be less than, and it can also equal 1. That's saying the same thing that sentence says. This is saying the exact same thing. It can't be negative. That means that it can't be less than 0, right? You can't have anything over here on the number line. And the fact that it can't be greater than 1 is the reason why we talk about improper fractions. Every single improper fraction in the world is greater than 1. Okay, and I mean, you could just put it into your calculator. I'll do one real quick just to see. Like if we have 15 divided by 6. 15 would be the numerator, 6 is the denominator, right? No matter what, if your numerator is larger than your denominator, you always have a whole number before your decimal, which is obviously greater than 1, right? So impropers, you cannot have as a probability of an event. Negatives, you cannot have as a probability of an event. Okay, and so I have something else right underneath here. It just says probability, say when probability. Oh, really good. When probability is represented as a percent. When probability is represented as a percent, it can be changed into a decimal. There will be homework problems where it's like, is this correct? Is this incorrect? And it might tell you, the probability of it raining, or the probability of the Raiders winning the Super Bowl, or the probability, it might tell you something, but it might actually have it written as the actual percent, right? So percent being, sorry, that's really messy, but you actually have a percent symbol next to it, right? The decimal, you're not going to have the percent symbol, right? You just have numbers and you're going to have a decimal, obviously. This is how that can be done. There's multiple ways, y'all. Say we have a percent and we want to change it into a decimal. I just have a capital P and a capital D. If you want to go from a percent into a decimal form, what we would do is we're going to divide it. So similarly, say we have something written in a decimal form, but we want to see what it is as a percent. To go from decimal to percent, we would multiply it. And both of these, I'm going to switch to a little thin purple so it's not too much. What I'm saying is it's by 100. If we have a little baby example. I'm not really going to write the whole sentence, right? But say it tells us that there's 173% chance that it's going to rain. And it's like, hey, could this actually represent a probability? You're like, hold on, percent, well, let me go ahead and let me change this into a decimal. Okay, we're in a percent form. And we want to go into a decimal form. So what I do is I type the 173. Okay, I did it right. I thought I typed something else. And then I want to change this to a decimal form. So I know for a fact, does this lie in between 0 and 1? So how did it tell me to do it? Okay, well, from percent to decimal, I divide by 100. So divide, bless you, 100. Welcome. This is actually equal to 1.73 whenever I change it into decimal form. The answer is no. This cannot represent a probability because it's greater than 1. Okay, so that's just a very little small example. If you're given something like this, and it's like, hey, can this represent a probability? You shouldn't have to change this into a percent. You shouldn't really have to do anything because it's very obvious that's bigger than 1. You should just immediately be like, no, it won't work, right? That's greater than 1. I can't have anything greater than 1. Okay. Okay, so that's really all they talk about right there for that. And then they are now going to explain complementary events. And it gives you 3 different formulas. They're the exact same formula, but they've been solved for different things. So there's a homework problem that it's like, hey, pick the 3 formulas that you can use for complementary events. You look at your notes, we have them all 3 written down. Okay. And what's crazy is I've never taught it this way. I always did it a different way. Oh, I made y'all something. So whenever, what did I do with it? Whenever I, right here, will you help me? There you go. Whenever I, there's only like 5 of y'all, so whenever I was typing this up, I literally had to type up a whole entire brand new one. I couldn't use what I used at TJC because we're using different formulas now. But go ahead and keep that. Don't lose that. I don't care at all if you use that on the test. Obviously, I'm not making you try to remember all of these formulas. Okay, you remember that other little packet of formulas also? You have that one as well, which is kind of more every single chapter. This is kind of more specific to this exam. Okay? I feel you kind of. Okay, then when you bring that back, I'm actually going to go ahead and explain it. Because obviously we're talking about probability, we're talking about cards, we're talking about dice, we're talking about coins, we're talking about all different kinds of things. And if you notice top left, right here, what does it say? Probability, right? The probability of any event occurring. I have it, oh, I love it, you forgot. I literally have it in between 0 and 1, and the fact that it can equal it means inclusive, right? And then, so this is going to be where we're going here, is the classical and the empirical. What we're fixing to do right now, y'all, go ahead and do me a favor. I don't know if maybe it kind of messed up, but do you see where it says the probability of a complement? And then it has this little bitty equation. It needs to end with a parenthesis. I think that was just something that kind of fell off. So you see right where we see the A's and the B's, right above that P of E, that needs to have a closing parenthesis, just so it's as proper as it can be. I didn't notice that until after I printed it. And then 3.2, we're going to talk about the second, or both of these right here. And then if you notice, here's the correlation coefficient and equation of the regression lines. We've done that. And then we're going to do combinations and permutations. And then here are different combinations of like rolling 2 dice. And then deck of cards. Y'all would be surprised. A lot of people don't know about a deck of cards as far as half being red, half being black, and the different suits. So that's where we're going. Okay, now let's go ahead and change to the complementary events. So, complementary events. In contemporary math, they learn about the complement of something. It's actually going to be like the opposite of something happening, and that's kind of similar to here with the complementary events. I'm going to draw something very similar to like a Venn diagram. Again, they learn about that in contemporary math, but just kind of do like a rectangle. And you just place a circle on the inside. We're going to name this rectangle sample space. Okay, now within this circle, we're going to call it capital E. This is our event. Okay? So we have this experiment, we have this sample space of all the different outcomes. We want to know what's the probability of this event occurring. So this would be the event that's occurring. The complement of an event is everything that exists within the sample space but does not exist in our actual event. So you actually write another capital E in the rectangle outside of the circle, and you put like an apostrophe. This is read E prime. That is a complement of E, the complement of event, whatever happening. They don't always use E. We could use all different kinds of letters, but this is just very generic right here. Okay, do I have another color? Ooh, let's see if this blue is pretty. Complement of event E. So that's what I wrote, complement of event E. And then I've got like 3 or 4 different little bullets that we're going to use to just kind of explain the different things here, okay? So when we talk about the complement of event E, visual representation was kind of the little Venn diagram, okay? So, okay, so the complement of an E. And I kind of said it, but we're going to write it again. The set of all outcomes in the sample space that are not included in this event. Okay, so set of all outcomes in sample space that are not included in, and then you could just write the capital E, or write event E. That's what it means to be the complement of something. Okay, it's like the opposite. Okay. Now, this is denoted Oh, okay, sorry, I saw a name and I was like, who is that? That's a student. Okay, this is denoted, which we kind of already have written it, but I'm right here. You do the capital E and you do the prime. This could be read the complement of E, or it could be read E prime. I like E prime. If I say the complement of E, I mean the same thing. Okay. So I thought that was going to bring it closer. I'll show more. There we go. Okay, and now here are, it's literally just different variations of one single formula. If you look on a piece of paper where it says probability of a complement, it actually gives you one equation. I'm going to give you all three different variations, which is just moving around different terms, okay? But doing that's actually algebra, and I'm not going to do that algebra for you, so you already have them all. Okay, so what we have is, I'll write that one first. Yeah. So the probability of in math is like multiply, but when I say of, like I'm like opening up the parenthesis. So the probability of E prime is equal to it just slowly moves by itself, doesn't it? E prime is 1, the number 1, and then subtract from that the probability of the event occurring, the probability of E. So they're saying like this whole sample space, right? The probability of something happening, if you do get, do you remember how on my little thing, I don't feel like moving my papers on this, I said it was inclusive. Okay, y'all go ahead and add this here. I know that it's impossible under 0. Oh, what word is used for 1? It's like a guarantee. It's like for sure. If I tell you the probability of you winning the lottery is 0, do you see how it's like that? Well, then it's impossible. It's never going to happen. All right. So the closer you get to 0, the more unlikely it is to happen. I cannot, for the life of me right now, think of what it's whatever word that we could think of that means that it for sure will happen. Certain. Yes, thank you. It is certain to happen. That is literally the exact word. You're the best person ever. It's Monday. So the probability of an event occurring, if I say, hey, the probability of blank is 1. That literally means 100% of the time it's going to happen. All right, the probability of rolling a number, right, 1 dice. Think of a die, and you roll it. It's 6-sided. The probability of rolling a number less than 7. No matter what I roll, it's less than 7, right? So that you would get 1. You would literally get the number 1 because it's 6 times of all these different outcomes. And if you do 6 over 6, which I'll show in a minute, when you do that math, you end up getting 1. The probability of being 1 means it's for certain. Thank you, Dominic. I owe you a coffee. If you want to know the probability of rolling a number over or higher than 7, and it's a 6-sided die, that's 0. That can't happen, right? That means it's impossible. So if we take that, the number 1 being certain, that's actually my whole sample space, right? And so that's why they have the number 1 right here. And if I want to know the probability of something not happening, I would take the number 1 and subtract the probability of it happening. That difference gives you the complement, okay? Now the different variations of this formula, they just kind of move things around and solve for different stuff. Okay, so we could also figure out the probability, like, so that's it not happening, right? E prime, it's E not. Complement means like what's not. Okay, it's not happening. This, let's figure out what the probability is of something happening. What is the probability of this event? The complement means that I want the opposite of it happening. So it's not happening, this is happening. And so the probability of an event occurring would be 1 minus the complement. And then, do you know how I told you the sample space, right? Like, kind of think about that as the number 1, right? say I'm looking at this and I take this number that is the complement and I add to it the actual event occurring. If I add both of those together, I should get the number 1. So that's like another variation of this. It's a formula basically, right? It's another variation of this happening. If you take the complement, sorry, not the complement, it really doesn't matter which one you write because it's addition. But say we take the probability of the event happening and we add it to the probability of the event not happening. Does it make sense that I took this whole entirety? I took everything. I took it not happening and I took it happening, and what I end up getting is 1. So those are the different variations of the complementary events. And there actually is another way to compute this, but when I was doing the like the notes and stuff, I actually liked the way that they did it. So I wasn't going to teach y'all 2 ways and confuse you. This looks like a lot, but it's really not that bad when you start doing the work. I'm gonna let y'all write that real quick. Take a drink of my monster. Not breakfast. So good when it touches your lips. Okay, y'all. I'm gonna come swish. Okay, where did I put that? Because I actually want to keep these together. Okay, now let's talk about all the different types of probability, and then we'll do an example of like using dice as one of the examples. And this is similar to the way that I would kind of word things in an exam. Is like these examples that are coming up. Okay, so types of probability. There's a lot of them. First one we're going to start with is classical, which y'all do have top left of your paper. It's also called theoretical. Classical or theoretical probability. I just put theoretical in parentheses the way that the key or the little, what's it called, does. What would that be, like a cheat sheet kind of? I can't spell this on my left. I think that's what it was. Theoretical. I don't know why that word's so hard. Probability. Classical, also known as theoretical probability. So, 2 bullets. The way that we know that we're dealing with classical or theoretical probability is each outcome in the sample space, right, is equally likely to happen. That's like when you roll the dice. And when I roll the dice, nothing is stopping 2 from being rolled unless it's weighted, which we're not talking about that in stats. You always just talk about like a fair die, right? Sounds weird. But every single side has an equal chance of being the one that you ended up rolling. Okay, that's what makes it classical theoretical probability. Okay, so each outcome in sample space is equally likely. Each outcome in the sample space is equally likely. Okay, and then we have the formula on the little cheat sheet, but this is the way it looks. So you have the probability of an event occurring is equal to, and you just do like a long fraction bar because we're going to write words. So you take the number of outcomes in event E. So it's like, what are you taking the probability of? Is it rolling a 1? Is it rolling even? Is it rolling this and that? That's what your numerator is. So the number of outcomes in, like, what are you looking for? What are you trying to find? So number of outcomes in event E that's your numerator. And then your denominator is the number of outcomes in the sample space, also known as like the total, right? So I've always been like the favorable. What are you looking for? What are we even taking the probability of? And then the denominator is like just the total. So, but the way that they'll write it is number of outcomes in the sample space, which is also known as just like the total of things that you're looking or working with. Okay, y'all. So some examples. Okay, so I have you roll a 6-sided die, find the probability of each event. And we're going to do 3 little examples. Okay, so you roll. If they are talking about a die, they'll tell you 6-sided, 12-sided, they'll let you know. Whatever sides your dice has, that's your sample space. Okay, because the sample space is all of the possible outcomes, right? When I rolled a 6-sided die, I have 6 different outcomes that could possibly happen. Okay, so if it's 12, your sample space would be 12, because those are all of the different outcomes that could happen. So that ends up always being your denominator, however many sides your dice has. So you roll a 6-sided die. Find the probability of output of each event. Okay, so first example. First, what I like to do, which you don't have to, sometimes I've been known to put it on a test, but if I'm talking about a 6-sided die, I don't know where my paper is. I'm talking about this. I'm talking about, right? That's one of my outcomes, is rolling and getting a 1. And then we have snake eyes. And then 3. And then 4. Why are my dice getting smaller every time? I should never draw squares. So that's my sample space, right? My sample space is literally rolling a 1, a 2, a 3, a 4, a 5, or a 6. Okay, first probability that we're going to find is, let me adjust all this. This camera just starts falling. Let me get this over here. Maybe that might help a little. Probability of event A. So P of A. And they use capital letters. And we're just calling it A because it's just first letter of the alphabet, first probability we're finding. So probability of A is rolling a 3. My kids should not be going outside. And they are. Rolling a 3. Yes. Okay, so we're like, okay, I could do this. I could actually figure out the probability of A, because that is going to be equal to, and then this implies that I have a fraction, right? And then what is the number of outcomes in my sample space? 6. So that's my denominator. Okay. how many times does the number of outcomes in event E. Y'all, with this, you're going to use E. They'll always use E. It's just like a formula, right? No matter what they give us here, I'm asking myself, if A, the probability of A happening is rolling a 3, how many number of outcomes is in this event, right? How many times can I roll the number 3? There is one number 3, okay? And so that ends up being your probability, but we're going to show it as a decimal. So you just grab your calculator, you do 1 divided by 6, and what we get, because we do round, it would tell you where to round it to. I rounded it to 3 decimal places. So y'all tell me what it ends up being. Does that kind of make sense though? You got, what are you looking for over total? Well, how many times did y'all roll what? A 3. How many 3s are there? There's 1. Over, what's the total? 6. But then what does that end up being whenever you put it in your calculator? Round it to 3 decimal places. Okay, now let's do this second example. And I might end up throwing a 4th one in here because I know that it's the type that I would put on a test, or it'd be more along the lines of, it's kind of making you have to do like 2 things. Okay, and we talked about this. What about this one? Say we have this other event. What we're going to do is we're going to call it probability of event B, because it's the second one we're talking about. Okay, say we have a probability of event B, and it is rolling a 7. That's like, okay, let me see. The probability of this event occurring would be equal to, okay, it's always easier sometimes to start with the denominator. What's my sample space? I'm still rolling a 6-sided die. I still have 6 outcomes total. That's my sample space. So that's my denominator. Look back at your dice. Okay, now in the numerator, I need the number of outcomes in this event. This event is rolling a 7. How many times can I roll a 7? None. So that's my numerator. There is no way, that does not exist. The outcome of rolling a 7 does not exist in this sample space. And then y'all, 0 divided by anything is just 0, which means what? Impossible? Does it make sense that the probability of rolling a 7 when you have a 6-sided die is impossible? Why? Because there's no 7. That makes sense? Okay. Let's do this one. We're going to call this probability of event C, because I'm just going in alphabetical order. And we're going to say that this is rolling a number less than 5. Why did I actually write the number 5 and not F-I-V-E? Kind of weird. I still won't write out, but I'm not going to do it. I didn't do a typo or anything. I just, some random reason, I actually put the number 5 there instead of writing it in words. Okay, so we can figure this out. The probability of this event occurring is equal to the number of outcomes in this event divided by the total, right, in the sample space. So the total is 6 because it's a 6-sided die. My denominator stays the same in all of these little examples for this exercise, right? And then rolling a number less than 5. How many numbers are less than 5? 4. Only because in math, whenever you use English, you really got to pay attention. Less than 5 means they didn't say anything about it equaling. You're right, it would be 5 if it said less than or equal to 5. Then it would be 5, 4, 3, 2, and 1. But you have to think about rolling a dice. If I roll a 1, I ask myself, is this less than 5? Yes. I roll a 2. Is this less than 5? Yes. A 3, a 4. When I roll a 5, is this less than 5? No, it's equal. So then I would stop there because obviously 6 is greater as well. So I end up having the number of outcomes in this event is 4. But that actually can be reduced to 2/3. Y'all, and this is me just kind of doing it on my paper. Once I get to 2/3, I would enter it in my calculator. If you do 4 divided by 6, you get the same thing. that I would get if I entered 2 divided by 3s, because your calculator is going to put it in the most reduced terms. Does that make sense? I gotta say that a lot. Okay, if I round this also, 6, 6 to 3, I get 6, 6, 7. And I want to play around some more with some English and math real quick. Let's do this fourth one. And and or are really important in math, right? And is like an intersection. And is like it satisfies both at the same time. Is it this and this simultaneously? The word or means it can be this or it can be that. Like either are fine, both is okay. But and or is important. I'll try to see if I can't get 5 on here. Let's do the probability of D occurring, and D is rolling a number less than 4 and even. Less than 4 and at the exact same time, it's also even. Okay, so the probability of D occurring would be equal to, what is my sample space? What's the total number of outcomes? 6. Okay, because I'm rolling, no matter what, I'm rolling the same 6-sided die. The total number of outcomes is 6 different rolls, right? And then I can look right here, and I can say, okay, let me just kind of play this in my mind. If I roll a 1, is that less than 4? Yeah. Is it at the same time even? No. So that doesn't count. That's not in my, what's it called? My outcomes of this event, this particular event, this sentence. I roll a 2. Is that less than 4? Yes. And at the same time even? Yes. So I have that, right? I mean, you can put a dot above it. Like, okay, I'm going to keep that one. I roll a 3. That is less than 4, but it's not even. I roll a 4. That's even, but it's not less than 4. So there was only one time that event occurred. And then we've actually done this before up here. We would end up getting 0.167. But you see how the word and literally means at the intersection of, it's like simultaneously this and that at the exact same time. Okay? Now I want to do an or, and I'm going to kind of have to smush it on here a little bit, but it is important, and this is how I would word things on a test. Now we are actually at the probability of event E, and let's say that this is rolling a number I'm going to do less than again because it's a smaller word than greater than. It really doesn't matter. Less than 3 or odd. Or. The word and in math is like an intersection, right? It satisfies both things at the same time. The word or is either or. It can be this, or it can be that, or it can be both. But or is like really all inclusive, right? Like it's not as picky as and. And is like, hold on a minute, like you've got to check both of these boxes. Or is like, check either, or both, it doesn't matter. Okay, so let me get my blue. So the probability of this event occurring would be equal to, y'all, what is my sample space? What's the total number of outcomes? I'm rolling the same dice, right? So I get 6. And sorry, I'm literally like writing over things, and I'm at the very bottom of the page. Okay, so rolling a number less than 3, or it's odd. So if I roll 1, I'm actually going to mark this one under here. If I roll the number 1 and I ask myself like these questions, is it less than 3? Yes. And then guess what? It also happens to be odd. So it satisfies both, which is fine. It's this or that or both. And you're invited to the party. Number 2, is it less than 3? Yes. Because it's yes to that, I don't care that it's not odd. Okay? Because or is either or. 3 is not less than 3, but it is odd. Right? So it gets included. 4 does not satisfy this and does not satisfy that. Didn't satisfy anything. 5 doesn't satisfy being less than 3, but it is odd. 6 would not be included. There's 1, 2, 3, 4 different outcomes in this event occurring, and I didn't know what I was doing when I was coming up with these words, but it ended up being the same as 3 as far as when we calculate it, we get 0.667. They all have the same sample space, and it is all just out of 6 different rolls. I mean, they're all going to be similar. The only one that really kind of stood out was rolling a 7. If I asked you what was the probability of rolling a number less than 7, if I got 6 different rolls, that would be in that event, and I got 6 rolls total, and then 6 divided by 6 is, so what's the probability of rolling a number less than 7? Is for certain. Probability equals 1, no matter what is going to happen. Okay? Let's move on to what? Empirical, which is statistical probability. So this was theoretical, right? Everything has an equal chance. Now what we're going to do is empirical. In parentheses it says statistical probability. This one actually, I don't even know if I even did it last year at all. It has like a little formula, so it doesn't seem too hard to understand. But usually it's like the classical or theoretical is taught more often. I don't know what colors I used on the previous page, so I'm just going to keep switching colors over here too. Empirical. Also known as or called statistical. Statistical probability. Okay, so what we have, so remember the classical, theoretical, everything had an equal chance, right? Now for the empirical or the statistical, this one, it has the word statistical in it, right? So there's got to be some kind of work that's put into it. It's based on observations obtained from probability experiments. You could probably just write based on observations, but I'm not talking. Based on observations it's like data has been gathered, right? And then we do the math on the data that we gather. Based on observations obtained from probability experiments. I should probably put white out on my my keychain. Oy. Okay. What it ends up being is the relative frequency of an event, or it's what it uses, is what I would kind of gather from this little bullet. Relative frequency of an event. And the way that we would figure out the probability of an event occurring using empirical probability, this would be equal to, when you do your fraction bar, in our numerator we put what the frequency of event E is, and then in the denominator we do the total frequency. I'm sure no one really remembers when we did like the frequency distribution, but the total number of all the frequencies in that section in here, we call it N. And then the frequency of the event was the cursive little f. And then there is a note here. Our N comes from the sum of all frequencies. We've seen this before, right? We have something, we collected data, we tally marked how many times something happened. Those tally marks were our frequencies. And then at the very bottom, if you add up all the frequencies, that would be the sum of them. And then we also gave it the name N because we used it within our formulas. Okay, let's do this example. This is like a comma, really really thick, bold, looking like a number 9 comma. And it's just saying that our n is the sum of all the frequencies. Either something got delivered, or my kids just keep going back and forth and back and forth. In and out, in and out. Okay. Example. So we're going to have 2 columns. One's going to be ages, the other one's going to be frequencies. First, let me go ahead and like kind of put the little example, like all the words of what it is that this data is representing. I think we just have one example. Yeah, we do. So I don't have to put the number. So social media users. Social media users' ages are listed below. What is probability the next person surveyed is 23 to 35 years old. I don't know why I did YRS. That's not even how it's written next to me, but that's what I just wrote. So we're going to have a list of ages and then the frequencies, and it's like, what's the probability that the next person that I happen to survey, that they're going to actually end up falling within that 23 to 35 year old range. So we can go ahead, and I'm going to do we have like 2 columns. The first column is ages, second column is frequency. And our frequencies, that's our F. So the different age ranges that I have is 18 to 22, 23 to 35, which is going to be where I'm trying to figure out if the next one's going to be in this group, 36 to 49. This is a frequency distribution. Sorry. This is a frequency distribution right here, but we're not having to do the work to set this up. They just give it to us. 50 to 64, 65, and over. And then after all these surveys have been done and all these tally marks have been taken and then like counted, there was 156 social media users that were between the ages of 18 and 22. 312 for the next group, 254 for the next group, 195 users that were 50 to 64, and then 58 users that were 65 or older. That would be my grandma, because I was on Facebook. Okay, so I didn't write solution next time, did I? Just solved it. Okay, I'm gonna switch colors. Really? So, I notice here that as far as the probability that the next person that I survey falls between 23 and 35, not everyone has an equal opportunity of being selected. It's kind of very much so at random, right? And I need to use the data that I've already gathered to figure out what, the statistical probability is that it would happen. Statistical meaning that we're using data. So that's how I kind of know that I'm using the empirical, and I'm going to do the F over N. So what I need to do, this is how I wrote it. I wrote the probability of, they didn't really call it like E or A or B or C or D or nothing. So I just said the probability of 23 to 35. So that's what I'm asking myself. What's the probability that the next person I survey is within this age range? And I know that this is going to be equal to, I can do my fraction bar, and I look back up at my, at my little formula. For my numerator, it says the frequency of the event. Does it make sense? This is like the first class, right? It's the second class of age range. If I go over the frequency of this age range, which is what I'm questioning, is 312. That's what it said. So get your F. These are my F's. Okay, here's the age range I'm worried about. Here's my F. So 312 is my numerator. For the denominator of the little formula that we have right here, it says to do the total frequency, which is what they're calling our N. And it says our N is calculated by doing what? Adding, getting the sum of all of the F's. So I'm going to kind of come right here. The sum of all my F's is, you get your calculator, and you would go ahead and you're going to enter in all of the different frequencies. And I get 975. So that's my denominator. And this example, we're just going to kind of keep rounding it to 3 decimal places just for continuity in the lesson. Read your homework. It'll tell you where to round it. Okay? This is approximately equal to, when I do 312 divided by 975. Okay, I don't have to round it 3 decimal places. This was exact 0.32. Okay, there is a 32% chance that if the next person that I survey, and I get their age and everything, they're going to fall in this age group right here. The sum of all the frequencies. So 156 plus 312 plus 254 plus 195 plus 58. If you notice, they're giving us our F. If they asked us what's the probability 65 or over, we would do 58 divided by 975. We kind of do have to figure out what the sum is, okay? And I think there's a handful of these on the homework where you see a little thing and it's like, what's the probability of this? Well, this is their frequency, or this how many times it happened. Add all them up and divide. If it says what's the probability, this is a little extra bonus one right here. What if it said the probability not? (36 to 49) age range. What's probably of them not being in 36 to 49 age range. So this probability, call it 36 to 49. Okay, so the frequency of the event occurring, this would be in that event occurring because it's not 36 to 49, right? 23 to 35 would be in this event occurring because it's not 36 to 49. This 254 I would not use because this is being in that age range, and I want to know the probability of it not being that age range, and I would include the 195 and I would include the 58. So the probability, if you add up everything except that age range, right? Because it's technically like the complement of this age range. If you add up everything else in the sample space that's not in this event occurring, I get 721 over 975. And that one, we would need to round it to 3 decimal places, and I've got 0.739. Or just round it to wherever they tell you. I've got a very likely chance, right? This point is like 74, say 75, close to 75% chance of it happening. So it's very likely that the next person that I survey is going to fall in another age group and not 36 to 49. So it's kind of like the different ways that the homework can work things. Okay, we found it happening, and so we only needed that one frequency, right? Because when does this happen? What's the frequency? Is this. When we wanted to find not being in this age group, we actually added up everything that's not in that age group, because that would be in this outcome. That would be in this event. Not in this outcome, sorry. That would be in that event. That would be all the outcomes in that event. And so you add up all those frequencies. Okay. I have one more type of probability for 3.1, and then I have like a handful of different little homework examples, and then we'll be done for the 3.1. And then y'all, I didn't really know how class was going to go today, so I have like 2 pages on 3.2, but I didn't really get that far because I thought they were going to cancel us. We started at 10, an hour and 25 minutes would be 11:25, which will be about 20 more minutes. And then we'll kind of see what we want to do. We'll put that here. Okay, we'll probably just go and do those pages. That's what I think. Subjective probability. When you hear like subjective probability, like in my mind, I think that, you know, it's going to rely on something. It's based off of something, right? It's subjective to blank. Our first little bullet, what's used whenever you do subjective probability or have subjective probability, is your intuition. How do you spell intuition? Oh man. Intuition. Like an educated guess. And distance. A doctor believes you have a 72% chance of surviving, right? And it's just his educated guess. It's just what he thinks. It's just, you know, after all the surgeries that he's done, he's not looking at the statistical data to come up with the probability. He just believes, right? He's just something in his gut that he just believes that you aren't going to survive. Either way, like that would just kind of be like, that's very subjective. Right, it's based off of his intuition and his thoughts and his educated guesses. Oh, I wrote it. I said it before I even looked. Doctor may feel patient has 90% chance of full recovery. So we're gonna go like that. And it's kind of like a little example. Sorry, I had it written down. I didn't have it on the other page though, so I just saw that. And I could not remember that word. Doctor may feel, right? Feeling is the big word there. Patient has 90% chance of survival. Okay. I don't know why I wrote this. Maybe just because I added something slightly different to it. I don't know if y'all want to write that. You don't really have to. You could add it to the little bitty one that we did on the previous page. On our little number line, the brackets here facing inwards mean that, you know, it can include the 0 and 1, and it's all values that would be greater than 0 and less than 1, because it's kind of like blocked in. It's an impossible probability. If you end up computing a 0, it means it's never going to happen. You have a certain probability. If you get the probability of 1, like it's for sure going to happen. You're going to get close to the 0.25 area. It's closer to the 0 than it is the 1, so it's pretty unlikely. Very unlikely that this is going to happen for you. It's 0.75, 0.80, 0.90. Like, okay, that's very likely, right? That's likely. If you end up, you know, getting a probability of 0.5. That is literally right in between it. So you have an even chance of it happening or it not happening. It's kind of like, I would prefer it to be closer to either end, but that 0.5 would be right in the middle. So I think the only different words there were like unlikely, likely, and even chance. Okay, let's do these little homework examples.